Thank you for coming to our design review. My name is Hemal Patel,
And I'm Stephen Lay.
and this is our Blaze CPU. On our agenda today is the baseline ISA and the enhanced instructions, as well as pipelining, including the overview, forwarding, hazard detection, as well as future enhancements to our design.
Alright, so moving on to the baseline ISA. So our memory structure follows that of the Harvard architecture, which means that each of the memory modules are separate from one another. As you can see here, the instruction memory, data memory, and the I/O, which is also a memory module, are each separate from one another. Each of these are byte addressable 1K by 32 memory modules. So moving on to our instruction formats, we have the R, I, and J type and their respective fields here. And our enhanced instructions that we put in are rotate left, rotate right. We use the same format as the R type, so we add it to the barrel shifter and we can shift or rotate the data based on the shift amount. Alright, so we'll move on.
So our major enhancement is pipelining. We have a 5-stage pipelining. The stages are IF, which is the instruction fetch, RF, which is where the decoding is done, EX, which is execute, DM, which is where the data or the memory access is done, and write back, which is where you write back to the register file. Here is how our pipelining works on a clock basis. On the first clock, as you can see, instruction 0 is on the instruction fetch, and when it goes to clock 2, instruction 0 will be at decode, and a new instruction will be loaded into the pipeline, and it keeps going until all 5 instructions are filled, and that will continue until all the instructions are executed. Our advantages with pipelining is that it has a higher throughput and can execute a set of instructions much faster than multi-cycle. This is our modified our modified integer data map, and here are the modifications we've done. We'll go by one, and this first are pipeline registers for the write back for the write address, and the write address is used on the write back phase. So over here, and the next modification we have to make is we have to pipeline the immediate value coming from the IR, so we can use it on the execution phase. We also have to pipeline shift amount, as that's also used in the execution phase. And DOut is no longer an output of the IDP. Instead, we have to pipeline it so that we can access memory at the appropriate stage. And this is where we access memory using this new output and mux out. Write back register is another pipeline register we need to create, and that will hold the data that you want to write to the register file. And here are all the forwarding muxes that we used. These will be explained in subsequent slides. Here are the pipeline registers. Starting here show the pipeline registers at the execution phase. Here shows at the memory access phase, and here shows at the write back phase. Using these registers, you can get a feeling of how the integer data path is broken up. And here we have our decode phase, where it uses the write port of the register file. Here we have our execute, which uses the ALU. Here we have our memory access, which uses 2 outputs to access the memory, as well as this output to access to the PC. And we have our write back, which uses the write ports of the register file. And that's all as it for the modifications to our IDP. Here is the modification we're going to do to our control unit. Our control unit no longer is a state machine. Instead, we have a bunch of pipeline registers with underlying logic. Here are our pipeline registers. As you can see, here are the control signals that move along the pipeline until they are used in where they need to go. Here are control units that set the first line of control signals, and going back here, the control unit logic actually requires the IR to set the signals to the appropriate values. And here is all the hazard controls. We have our hazard detection unit, our forwarding unit, and our interrupt state machine that we'll talk about when we reach in later slides. That's it for our control unit.
Can you go back just one? The control unit logic up in the upper right hand. You didn't. mention that one, no.
Oh, this is how flags work. So the flag,
The very rightmost
very right.
circle,
one?
yeah, that guy.
Oh, okay. So both of these are basically the same thing. These control the PC and IR signals. The hazard detection, which we'll get into later, it only controls these signals, so we just split it up to make it look.
But are those signals coming out of that section also registered
Oh
somewhere?
yeah, they are registered. I'm sorry about that. Yeah, these are supposed to be registered.
Okay, no problem.
This is an example of how our control unit logic works. Just to show here, it just uses the IR to set the signals, and this is the first phase of the pipeline where it sets all the control signals. As you can see, as you mentioned, yeah, these are also registered. They don't directly go out.
Yeah.
So due to the nature of pipelining, there are many things you have to consider. One of the main things that you have to consider are data hazards. As you can see in this illustration here, we have an instruction that doesn't add to register 5, and all the 4 subsequent instructions are dependent on this register 5. As you can see from the red lines here, that they point to where these instructions will be accessing the register file to get R5. However, these 3 instructions are trying to get R5 prior to this instruction's write back stage, meaning that the data in these registers are not yet valid. For this one, it is valid because it is 1 clock after the write back phase. So to begin dealing with these 3 hazards, we start by modifying our register file. So the difference between here and here is up. In this, we changed our register file to save the data on the negative edge of the clock. In doing so, since this instruction accesses the data on the positive edge of the clock, the data is actually ready during this write back state and can be accessed from this register file. In doing so, this specific instruction is no longer a data hazard. However, these 2 still are because you cannot bring the data back. So what we do instead is we forward from the pipeline registers. Because we're doing pipelining, the data of register 5 can be found in this pipeline register after this execution phase. Using that to our advantage, we can forward from this pipeline register to the execution phase of this instruction, and likewise this pipeline register to the execution phase of this instruction. In doing so, we resolve our data hazards. Alright, and similarly for forwarding, you also have to forward for memory access. So just like before, this instruction is good because it takes the data from the register file after it's read back. This is good now because of our modifications of saving the data on the negative edge of the clock, and these 2 instructions are forwarded from this pipeline register to their respective locations. This can be illustrated in our integer data path. For forwarding to the execution state for 1 clock away, there are 3 possible registers that you would want to forward, which are the ALU out, the low, and the high, which are forwarded to these muxes, the S and the T inputs of the ALU, indicated by the red arrows. And likewise, if you would to forward for 2 instructions away, you would forward the write back register to the S and T inputs of the ALU. And as well as for memory access, you would have to forward this write back register to these 2 muxes, but depending on whether it is 1 clock or 2 clocks away. So how exactly do we do pipelining here? So here's an example where we do an add, and then this next add is dependent on this. So what you have to do, and this is with respect to this current instruction, you check the current RS, which is this, the previous instruction is RD, and you check if the previous instruction wrote to the register file, which means that this enable is on, and the select actually wrote to address RD. And if all of this is true, then you would select the forwarding mux to grab the data from the pipeline register for this instruction.
Same thing for the RT decision, right?
Yeah, this is just one of many examples.
Yeah.
So here's the verification for our forwarding. So here are here's the assembly, and here are the expected results. So we'll start by loading registers 1, 2, and 3 with 1, 2, and 3, and then we start adding the constants of the register file. So as you can see, these 3 instructions are dependent on this instruction, where this is the RS side, and the previous instruction, which is an add, means that it wrote to RD. Same with these, however, you're using the RT side, and this previous instruction also wrote to RD. And the expected results, again, are right here, and here are the actual results of what we got, and sure enough, they're the same. So, and to be thorough about it, you have to also check if the previous instruction wrote to RT. So So the difference here is we have an add immediate, which means this instruction writes to the address of RT. And this is the RS side, and this is the RT side. And here are the expected results, and here are our actual results. And they are the same. Same with forwarding for memory access, specifically Starward. So these instructions you forward first for memory access when the destination register is RD. So there's RD, there's your data that you're forwarding, and then here's this, and then this is the add immediate, so you're forwarding when the previous wrote to RT. So there it is, and so the expected results would be this right here, and here they are. Then I'll throw it to Hemel for the next part.
Okay, so I'm going to go over the hazard detection, and to show that we need a hazard detection, we're going to assume a jump, like just any arbitrary PC change happens, and instructions follow that which are retrieved from the IR. If the PC changes at the register file, then instruction 1, the PC would actually change here, meaning this instruction would not have the correct IR. This means that this specific instruction is invalid specifically when you load the PC during the register file stage. Also, if you were to load the PC during the execution phase, then both of these instructions would be invalid. If you were to change the PC at the memory access phase, then these 3 instructions will be invalid. In order to deal with these invalid instructions, we have to change them into no-ops, is how we went about it. So there's 2 ways to go about it. One way is a flush, another way is a stall. How flush works is that once the PC actually changes, you flush the pipeline, meaning everything between your current instruction and the jump, all the control signals for those specific instructions are changed to no-ops. The second approach is stalls, where once the control unit detects some kind of PC change, for example a jump, then we set the PC to not change, and we set the IR to do no-ops until the PC actually changes, and once the PC actually changes, then we continue with the pipeline. So our design actually does not use flush. It turns out that flush and stall do have the same timings for everything except one case, and that's branch fail, and we'll go over that. And the reason why we only did stalls is because it was just simpler to implement, and if we wanted to do flush, we definitely could. We just need more time, and it would definitely improve it's one of our future enhancements.
Are you going to talk a little bit about the difference between when you detect your conditional branches and then fail or pass?
Yeah, I will talk about
Okay.
branch fail and pass.
Okay.
Okay, here are the hazard detectors that we're going to go over. First of all, we're going to start with the load word, and then we'll go over the control hazard.
So, alright, back to data hazards. So we got a load word right here, and subsequent adds that are reliant upon the data of the load word. So as you can see here, what we did before, so these instructions are good to go. However, if you see up here, this arrow right here, this forwarding cannot be done. This is because the data of a load word is only available after the memory access phase.
Right.
Meaning that you cannot forward backwards to the execution phase. So what we do is we insert a stall in between the load word and add, pushing the add further by 1 clock so that you can do the forwarding from this pipeline stage to the execution phase of this add.
Okay, so going over the rest of the control hazards, there's a few, how our implementation of how we went about it is, first of all, we wait until, we continue until we detect a PC change, meaning like a jump or a jump register happens. And then after we detect that of a potential PC change, then we stall until the actual PC change actually happens. So here are the number of stalls for the respective PC changes, as well as interrupt and return interrupt, which uses states. We'll go over that in subsequent slides. Here is our instruction unit. We'll show all the modifications right here. So we had to pipeline the instruction register because branch and jump and link actually change the PC actually changes when it's at the execution phase. So you have to pipeline IR since we're going to clear IR, which I'll go over right now. Why you clear IR is because of the IR no-op. So our IR no-op is our stall, or how our stall works. So it clears the IR, and what clearing the IR does is it decodes as a shift left logical of register 0 by 0 to register 0, which does nothing, which is what a no-op should be doing.
Right.
And PC decrement is also another control word we have to add. This is specifically for the interrupt. We'll go over why we need that during that slide. Here, just going over the inputs to the mux of the PC. We have, this is for branch. This is for jump and link up here. This is for the input. For register, for jump register. Here we also have a normal jump, because this one actually uses the IR directly, as it happens in decode. And the last case is wired directly from memory, and this is for to retrieve the specific PC from memory when doing interrupts and return from interrupts. And that's it for the changes. Moving on to how the jump is executed. Basically, during decode, the PC changes, and it also sets the IR to no-op, so that no other instruction will execute afterwards until the execute phase, and it actually resumes once you hit the execute phase. And this jump only has one stall using this approach. And how our logic works is that all you need to do is check if the IR decode opcode is a jump, then you set these specific controls, as well as the default controls to the pipeline registers. For our jump and link, we have 2 stalls. The reason we need 2 stalls is that we need to give time for register 31 to be written into the register file. And since this has 2 stalls, we need 2 different cases here. One to check IR decode opcode if it has jump and link, and the second to check if the IR execute opcode has the jump and link. How our jump register works is that it requires 3 stalls, because that's how long it takes for it to go through our IDP. Here are the specific register RTL of how it goes through our IDP. And we need 3 specific cases, as there are 3 different stalls for the different PC and IR no-op cases. And going through the branch success, it only uses 2 stalls. The first stall, it stores, it gets RS and RT, and then on the second stall, it uses those 2 registers, uses the ALU to get the appropriate flags, and executes. And in this case, it does pass, and meaning the PC does change. And so here, if we look at our cases, on the second case, not only does the execute have to equal any of the branches, but it has to equal one of the success conditions of that branch. And moving on to if it's a fail, it's only a 1 stall, and what happens is that as soon as it checks that it's not actually branching, it actually just keeps the same PC and IR. So this actually ultimately leads to just 1 stall needed. It will fail this branch check and just have the default instead. So this is what I was talking about with flush. Flush actually, since you won't actually have to change the PC. A flush would use 0 no-ops, so you'd actually this instruction would be faster if you use a flush. Okay, going over with interrupts. Why do we use states for interrupts? Well, interrupt actually does multiple ALU operations rather than having to put multiple ALUs in our execute state. It's better to do it as like a kind of state machine. It also does multiple writes to memory. So it's actually, and also it's not actually an instruction, so you can't check the IR. So the best thing to do, we did states. 3 of the states do 3 different operations, starting with loading the PC into memory, loading the flags into memory, and updating the stack pointer, as well as changing the PC on the 3rd. And on the 4th and 5th is 2 no-ops. The reason why is we need to wait for PC to finish updating. Note that this takes priority over all other instructions. When you go through the control unit, you're going to find that you're not actually executing the current instruction. You're going to be executing the interrupt instead. So it turns out, and PC is also pointing to the next instruction. So you actually have to decrement PC so that when you store the PC, it points to the current instruction that you haven't executed. So that's the main reason why we have PCDEC. Also note that interrupts cannot be done during a stall. If you're in between a jump or a branch, it has to wait for that to finish before you can actually interrupt. This is to prevent any potential errors if you were to actually interrupt in between a branch or a jump or something. Okay, going through a return from interrupt, that also uses states. It also does multiple operations, and it has 5 separate kind of instructions, so it's best to do it in states just like interrupts. So starting with the first state, it loads the flags from memory, it loads PC from memory, and it updates the stack pointer, as well as 2 no-op operations. And those 2 no operations are done to wait for the stack pointer to be written to. Here's our verification. We'll start with the jumps. As you can see, you jump over the break, which writes to register 1, and as you can see on the simulation results, register 1 is written to. You check on our second case, we have our jump and link, which jumps to our call function, and our call function writes to register 7, and on our simulation, it looks like it succeeded. And then after that, it does a jump register and writes to register 2 after it returns back from the jump and link. And then we can see it writes to register 3 when doing the branch unequals test. It tests R0 and R1. R0 currently is 0 and R1 currently is 1. They're not equal, so it should branch, and it does. And it jumps over the break, writes to register 3. Then we check the branch fail, checks the same 2 registers, except if this branch equals. And it actually failed, the test failed, so it doesn't go to the branch and writes to register 4. On our load word test, we take the value from memory and write it into register, and as you can see, that succeeds as it writes to register 5. But the real thing we want to check is if the stall works. So we have an add operation which uses the register that we just received to do the stall case, and we see that register 6 does have the appropriate value, as we do add register 5, which is 5, and register 1, that is 1, and gives us the added value of 6. And finally, to see if our interrupt works, as we did set the interrupt up here, it should have interrupt. We have it to interrupt 10 clock cycles after, so it should have happened between 1 and 2. And it is written to register 8, and that means that the interrupt, it did pass through the ISR. And that's it.
So we're talking about pre-chance. So what we want to do is optimize our pipelining. So we could, what Hemel was talking about, we could add the flushing case instead of stalls. What we could also do is add branch predictions instead of just doing stalls or flushes. And we would also probably want to add vector operations, like the SIMD unit to our thing, and that's it.